MATPLOTLIB is the main Python library to produce publication-ready plots. Its history dates back to the early 2000s, when it was first developed as a free and open-source alternative to MATLAB. With 15 years of further development and testing, MATPLOTLIB is now a highly reliable and powerful tool which we can use to produce virtually any plot. In this lecture, we're going to see how to create the most basic plots. We start by importing NumPy and pandas, which will be used to handle and generate the input data. Then we import matplotlib as MPL and the collection of matplotlib functions called pyplot as PLT. We use the matplotlib magic command to specify that we want the plots to be embedded as static images in the notebook. The alternative is to write %matplotlib notebook, which results in interactive plots embedded in the notebook. We use pandas to load the Eurostat dataset on waste generation that we had cleaned and saved as an Excel sheet in a previous lecture. We rearrange the data as a multi-index data frame, and we select a cross-section of the rows to obtain a series. The series has as indexes the years, and as values the total amount in kilograms per capita of non-hazardous plastic waste generated in Sweden. Indexes and values are then stored in two separate NumPy arrays. These are the x and y values that we want to plot. We use the plot function of pyplot, passing x and y as the first two arguments. This function generates, behind the scenes, the figure object and the axis object. For more advanced plots, it is often useful to retrieve these objects using the functions getCurrentAxis and getCurrentFigure. Alternatively, figure and axis can be generated explicitly. This approach gives us more control on the plot, and we will use it in the next lecture to create composite plots. Here we highlight that when we create the figure object, we can specify the figure size passing the width and height in inches as a tuple. Instead of passing x and y as separate arrays, we can simply pass the series, and the function will infer the x and y arrays. Now let's see how to customize the plot. We can pass the color, the marker, and the line style as separate arguments. For the marker, we choose between O for a circle, S for a square, capital D for a diamond, V for a triangle pointing downward, and many more. For the line style, we can choose between hyphen for a solid line, hyphen hyphen for a dashed line, colon for a dotted line, and hyphen dot for a dashed dot line. These parameters can be condensed into a single string passed right after the data argument. Other parameters which we can customize are the line width and the marker size, conveniently abbreviated as LW and MS. The axis labels can be set using X label and Y label, whereas the axis ticks and tick labels can be customized with X ticks and Y ticks. With these functions, we can also control the font size and the distance of the labels from the axis. It is useful to know that if the figure and axis objects are created explicitly, these functions have different names and behave slightly differently. X label and Y label are called set_X label and set_Y label. X ticks become set_X ticks and sets the position of the ticks only. The labels are set instead by the set_X tick labels function. Additionally, we can set the limits of the axis with xlim and ylim, and we can add a legend. To do that, we pass a string for the label parameter of the plot function, and then we call the legend function. We can specify if we want a title for the legend, if we want a frame around it, and we can customize all other aspects of the legend as well, such as the length of the handles. Despite the simplicity of this plot, we have already seen that the number of parameters that we can control is very large. Typically, we want to decide on a set of parameters and stick to that for all our plots. To that end, it is convenient to modify the default parameters once and for all in the beginning of the notebook. The default parameters of MATPLOTLIB are stored in the RC params dictionary. Scrolling down, we find the font size for the axis labels, the size of the plot, the legend parameters, etc. We can modify them using the function update. To restore the default parameters, we call RC defaults. When we call plot within a loop, each line is colored according to a sequence determined by the default property cycle, which can be found in the RC params dictionary. This list of 10 hexadecimal colors is the category 10 color palette, originally developed for the Tableau software and is called Tab 10 in MATPLOTLIB. Other palettes are available and can be accessed with the getColorMap function. For example, here is a palette of 11 colors and one of 20 colors. Additional information on color maps can be found in this tutorial. If we want to use a single color from a given qualitative color map, like Tab 10, we can do so by creating a color map instance and writing in parentheses the position of the color in the palette. The function returns an RGBA tuple in arithmetic notation. The first three values are the fractions of red, green, and blue, whereas the fourth is the alpha channel, which determines the opacity. To use a given color, we can pass a hexadecimal code or an RGB to the color parameter.